All right, I think we're live. Afternoon, Year 12. Sorry I couldn't be there today, but after your learning tools earlier in the year, I thought I'd be inspired and try and do a quick online, or not online, but, a video recording of how to solve the hardest equilibrium type of question that we've encountered so far. So on this page, you'll be able to see I've just put like type 1, you just sub in equilibrium constants. Type 2, you have to use a rice box. Type 3 is a little bit harder because you aren't provided with any equilibrium concentrations, and you're normally provided with one initial concentration. But the thing is, you have to work backwards, okay, from the equilibrium constant to work out the equilibrium concentrations. So don't mind that noise, that's just me smacking my pen to try and get it to work. Okay, so let's have a look at how we solve this type of question. So, firstly, shout out to Chem Team. Okay, that's a really good online website. I would recommend going and using it. They've got good questions, good examples, some funny chemistry jokes and stuff. It's a good place to go. That's where I got this question from. So, we've got our equation. So, first thing I might do, equilibrium question, I'm going to do the equilibrium expression. So, KEQ equals products over reactants equals NO squared. So the squared comes from the molar coefficient, and then the reactants are N2 and the other reactant here O2, and their molar coefficients are 1 and 1, so that's just 1 and 1 there. Okay, great. And we know that this equals, we've been given what the Kc. Okay, so Kc equals KEQ equals K. It's all the same thing. It's just another way of writing equilibrium constant. So the Kc, or the equilibrium constant, equals 0.0153. Okay, so this is going to be our useful expression that we'll come back to later. Let's have a look at what other information they've given us. At 3000 Kelvin, K's for Kelvin. That doesn't really mean anything. It's just telling us that, or it's just reminding you that an equilibrium constant is only constant at a particular temperature. And for this case, it's 3000 Kelvin. You can notice that I completely ignored all this mumbo jumbo up here. It's just unnecessary information that's kind of interesting but not relevant to answering the question. So it's good to be able to just block out information that you don't really need at this point. Okay, we've got the equilibrium expression. It's an equilibrium concentration calculation question, so we have to do our rice box. So R for reaction, which is N2O2 to NO. Really important that you include the molar coefficients there, because they're going to come in handy in a moment. I for initial concentrations, C for change in concentrations, and E for the equilibrium concentration. So the concentration of these three substances at equilibrium. Now, initial, let's have a look at the initial concentrations. If 0.3 moles of pure NO is injected into an evacuated 2-litre container. Okay, now be careful. You don't want to just go put 0.3 in here, because that's not the concentration, that's the number of moles. So we need to do the concentration initial for NO equals moles divided by volume equals 0.3000. That's a lot of zeros, divided by 2.000 equals 0.1500 moles per litre. So we can put that as the initial concentration for NO, 0.15. Okay, because it said pure, that's a clue to say that these are both 0. Pure means it's just this, which means these are both 0. Cool. Okay, next, equilibrium. It has not given us any equilibrium concentrations, which means we're going to have to do a little bit of funky algebra to represent them. So this change, C for change in concentrations, is going to be very, very, very important now. And this is where the molar coefficients come in as well. So in this case, we know that because this is all we've got to start with, as the reaction proceeds, this is going to decrease in concentration. So we know the change is going to be negative because it's going to decrease. And because this is a molar coefficient of 2, we can say that it's going to be a change of minus 2x, where x is the change that would happen if there was just for a 1 molar ratioed substance. 1 molar, I mean like it's got a 1 in front of the balance in the balanced chemical equation. So we've got minus 2x for this one. Now this has got like an imaginary 1 here and an imaginary 1 here. So as this decreases by negative 2x, these will both increase because they're being made by plus x. If this was a 2 instead of a 1, it would be plus 2x, but it's not, it's a 1. So we're just going to do plus x. Okay, so this is our change. Plus x for this one, plus x for this one, minus 2x for this one. Using this change, these changes, we can write an algebraic expression for what the equilibrium concentrations are. So for this one, the equilibrium concentration would be 0.15 minus 2x. This one would be 0 plus x, which would just be x, and 0 plus x, so it would just be x. We have now got an algebraic expression for each of the equilibrium concentrations. This means we can sub this algebra into this equation up here and solve for x, which is what we're going to do now. So 0.0153, that was our equilibrium constant, Kc or Keq, equals NO squared over N2 and O2. So this equals NO. So the NO's this one, this is NO. So it's 0.15 minus 2x squared over N2, x times x. So really this equals 0.15 minus 2x squared over x squared, 0.0, oh, come on, pen, 0.0153. Okay, now, mathsy people are probably thinking, oh, okay, do I need to use the quadratic formula expression thing to solve this for x? You could do that. However, it's not expected in the chemistry HSC that you can solve quadratic expressions like this. The reason I picked this example is because you don't need to do that. There's a bit of a trick we can do. Because you can see that this is squared and this is squared, if we square root this whole side, it gets rid of those squares. You just have to remember to square root this side as well. Otherwise, you'll get the wrong answer. And then if you square root one side, you have to square root the other side. So that's what we'll do. If I throw those into my calculator, so square root of 0.0153 equals 0.123. I'm just going to do dot, 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 because there's a lot of decimal points there. Dot, dot, dot means there are a lot more decimal points than I know the numbers of, but I can't be bothered to write them down. However, I will use them all in my further calculations. Equals, because we've square rooted this, we've now just got 0.15 minus 2x over x. From here, it's a pretty straightforward solving, so we'll take this x up here, 0.123 dot, 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 x equals 0.15 minus 2x. We'll plus the 2x onto this side, so 0.123 dot, 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 x plus 2x equals 0.15. We'll just add these two because they're both just like something, something, and x's, so we'll just add them. So that's 2.123x equals 0.15, and then we can solve for x by just dividing this by this number. So answer plus 2 equals that, and then 0.15 divided by answer equals 0.0706 dot, 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 because I've got more numbers, but I'm not going to write them down. And x, so x represents a concentration, okay? It represents the change in concentration, and then we can use it to represent the equilibrium concentration, which means our units down here should be moles per litre. Okay, so we've solved for x. The question wanted us to find the equilibrium concentration of NO, which is this one. So concentration of NO Uh,